Okay, so we're continuing in physics. Yesterday we went through 13. We're going to do 15 now. There, can you please do 15?
Calculate the Earth's gravity force on a 75-kilogram astronaut who is repairing the Hubble Space Telescope 600 kilometers above the Earth's surface, and then compare this value with his weight at the Earth's surface. In view of your result, explain why it is said that astronauts are weightless when they orbit the Earth in a satellite such as a space shuttle. Is it because the gravitational pull of the Earth is negligibly small?
Okay, so basically they're saying, what's the weight? When the astronaut goes 600 kilometers above the Earth's surface, person's going to feel lighter. So what is his or her apparent weight? Okay, the reason it changes is that G changes, right? So there's two ways you can do this. You can do it basically in one step using Newton's law of universal gravitation. So why don't you do that? Use Newton's law of universal gravitation to get the force between him and the Earth. That gives you his weight at that location, or her weight. So you're just plugging in and calculating. So we have universal G, which is 6.67 times 10 to the negative 11. You have the mass of the Earth, is 5.98 times 10 to the 24. Then you have to add in mass of the person and then the R squared. So the R is the radius of the Earth plus 600 times 10 to the 30. Remember, you have to put it in meters. And then you just enter it into your calculator.
radius is just this.
It's the sum of these two.
Oh.
The radius of the Earth plus 600 times 10 to the third. We get it if we go on to 17. This whole thing here. So it's just 22.9 times 10⁻16 divided by, let's add that whole thing at 6.378. That would be plus 7. You should get 610 newtons. So you should have gone G, 5.98 times 10 to the 24, the mass of the astronaut divided by, and now you have to put these in parentheses correctly. You can't close your parentheses. You're dividing by the whole thing. You should get 610 newtons. Then you get a person's weight. Okay, so then the mass of the person, the weight of the person is 735. Okay. Now, this is the gravity force. But the satellite and the astronaut have the same acceleration, so the astronaut's apparent weight is going to feel like 0 because the astronaut is going to feel like he or she is falling. We went into that in the PowerPoint. Explain why it is said that astronauts are weightless. It's not because the gravitational pull of the Earth is negligibly small. You got the gravitational pull of the Earth at 610 newtons. It's because they both have the same acceleration. They're falling together. Okay, let's do 17. So we're looking at gravitational potential energy. We went through that equation yesterday. The U is equal to negative G mm over R. I had you calculate the escape speed of Earth. Okay, so now we're going to look at a different escape speed. Alyssa, can you please read 17?
Also results of the conclusion to calculate the state hearing for the spacecraft. A from the surface of Mars and B from the surface of Jupiter. Use the data from appendix and see the data. So that is a escape scheme for the spacecraft independent of the spacecraft mass.
Okay, so we went through the equation for escape speed. You have it in your notes. You use the appendix to get those values to plug in to get the escape speed of planets.
There was some people were calculating. I couldn't get the number of people that didn't have the ground.
Yeah, and it's kind of by the astronauts, they also. So,
So is that
and you scroll the bottom. So, if you just a second, enter, then
look like this one when I think this?
600 plus, what should be towards 6.37 times 10 to the 6.
I see.
Kilometers. So if you remember from yesterday, we went through the equation for escape speed. It was this, square root 2 gm, mass of what's being orbited over r. So you're looking up the mass of those planets. You have to get the mass of Mars and the mass of Jupiter in your appendix. If you get that, see if you can answer C. Okay, so you're just entering the values in the mass of Mars, and the radius of Mars. The mass of Jupiter and the radius of Jupiter. Now remember the number we got yesterday, which was 1.2 times 10 to the 4th meters per second. So you should get a reasonable answer. That was the last answer. Okay, so we have first the mass of Mars is 6.42 times 10 to the 23, right? You can see that in the back of your book. The radius is 3.39 times 10 to the 6th. Just entering it into the equation. Okay, then we have the mass and the radius of Jupiter. So you're just plugging them in to figure out what is the speed you have to reach to escape the gravitational pull of Mars. What's the speed you have to reach to escape the gravitational pull of Jupiter? When you finish, just go on to 19. Okay, so the whole thing is under the square root sign. You should get 5.03 times 10 to the 3rd meters per second, or just over 5,000. Renee, did you get the escape speed Jupiter?
Yes, I got 6,216.26.
Good. Okay, everybody understand? We're just plugging it in to get those escape speeds. Okay, now when you finish, just go on to 19 and read that to yourself. Okay, so in 19, there's multiple ways you can do that. A planet orbiting a distant star has radius 3.24 times 10 to the 6 meters. Escape speed for an object launched from this planet's surface is 7.65 times 10 to the 3rd meters per second. What is acceleration due to gravity at the surface of the planet? So that's your small g. They give you the radius and they give you the escape speed. What can you figure out from that? Mass. That's like probably the most straightforward way to do it. You don't have to do it that way. You actually could skip calculating mass just working with the algebra, but anyway, we're going to calculate mass. So you know the escape speed, you know the radius, you can plug in and solve for mass. Once you have mass, you can get your g. You finish with 19, you can do 21. Okay, so you just plug in the numbers they gave you, square both sides, isolate your m. So if we square both sides of the equation, we get v squared is equal to 2gm over r. You're isolating your m, solving for the mass of the planet. Once you have the mass of the planet, you can just plug in to get your g here. showing you how I did this. I isolate the M. Okay, so you have v squared times r over 2g gives you your M. Did you get the M, Nevaeh?
Not yet.
So we're going v squared times r over 2g. Alyssa, did you get your M? What'd you get?
72,000.
Should be really a big number for mass of a planet. So did you put everything in parentheses? So it should be like this.
So maybe 24,000.
7.65 times 10 to the third squared times 3.24 times 10 to the sixth divided by 2 times 6.67 times 10 to the minus 11. You should get 1.42 times 10 to the 24. Once we have that, we can get our G, because we have that our G is GM over R squared. You should get a G of 9.03. One 1.42, not 1.24. So now, when you're done with that, go on to 21, just read that to yourself. Okay, so in 21, it says for a satellite to be in circular orbit 890 kilometers above the surface of the Earth. Okay, that's your altitude. So that is not your R. What orbital speed must it be given, and what is the period of the orbit in hours. Okay, so yesterday we talked about circular orbit. We had our two equations to work with. Where did it go? Okay, so your two equations were the V is equal to the square root of GM over R. And the other one was the V is equal to 2 pi R divided by the period. Okay, so first they're asking us the speed. You're just plugging in. You know the mass of the Earth. You have to get the altitude. You have to get the radius, which is going to be the sum of the radius of the Earth plus that altitude. Okay, so your R is the sum of the two. The R is the distance from the center of one to the center of the other. This is above Earth, so you know the mass of the Earth. Now notice that they said kilometers, which is why I put it as 8.90 times 10 to the fifth. Or you could have done 890 times 10 to the third. Gives you 7.26 times 10 to the sixth, but you could just enter in the sum of the two. After that, we're getting the period. Then you're going on to 23. Nevaeh, did you get the speed?
Yeah, maybe. Sure. Yeah.
Did you get 7.4 times 10 to the third? 7.408 times 10 to the third. Did you get this? Now, in B, we're just isolating our t, so our period is therefore 2 pi r divided by v. So you just enter it in to get your period. So we're just entering it into pi r divided by v. We just got the v. Okay, so you should get 6,158 seconds. You're just entering in the same r dividing by the v you just got. Now in 23, one way to do it is to get the mass. You can avoid that if you just work with the algebra equations. Two satellites are in circular orbits around a planet that has radius 9.00 times 10 to the 6 meters. One satellite has a mass 68.0 kilograms, orbital radius 7.00 times 10 to the 7 meters, and orbital speed 4,800 meters per second. The second satellite has mass 84.0 kilograms and orbital radius 3.00 times 10 to the 7th meters. What is the orbital speed of this second satellite? Okay, they're orbiting the same planet, so you can use the information from the first one to get the mass. Since circular orbit, you're using your circular orbit equations. Whenever circular orbits come up, you're using those two circular orbit equations. So use your circular orbit equation to get the mass. Okay, so since they gave us the r and we know the speed, you can solve for the mass of the planet, just like we did in the previous problem. We're solving for the mass of the planet. So we're plugging in, 4,800 is equal to GM divided by 7.00 times 10 to the 7th. So we square both sides of the equation. Isolate your mass of the planet. Again, we isolate that M. So I have V squared is equal to GM over R. V squared R over G is equal to M. I just plug in and solve. When you have it. Once we have that, we can get the speed of the other planet because we'll know the mass using the same equation. Nevaeh, did you get the mass of the planet? Dakota, did you get the mass of the planet?
I'm gonna write 2.42 times 10 to the 25th.
Okay, good. Okay, I have 2.418 times 10 to the 25th. Now, using that, we can easily get our speed. So we plug that in. We get 7,330 meters per second. Once we get our mass, we just plug in the mass. Okay, for homework, we're just going to do 16 through 22. Okay, just 16 through 22. You have your other math homework as well.